Okay, we are finishing up the 3.9 notes. We are talking about linear approximation. And basically what that is we looked at like a curve, and if you zoom in far enough, it really takes the shape of a line. So we can use the slope of the tangent line, which becomes like indistinguishable from the actual curve, to estimate points around that point of tangency. That's basically what the linearization is used for. So when they ask you to find the linearization, you're really just finding the equation of the tangent line, which you need the slope and a point. And then the only thing to do to really make this like a linearization is rewrite it as L of x. It's just like a notation thing, and then solve it for y. Okay, so we started this problem by finding the linearization of the sine curve at pi over 3. So now we're going to use it to approximate the sine of 1.25. So that's part B here. So I'm going to use this linearization equation, plug in 1.25, to approximate this. I don't have my graphing calculator pulled up, but I got about 0.9674 ... Okay. So just type that in your calculator. And then C says kind of find the error. So again, this is like using the tangent line to like approximate what that is, because 1.25, how does that compare to pi over 3? Well, pi over 3 is what? 60? I guess that's not super close to 60, but we can actually find the sine of 1.25, right? So to find its error, basically you're going to figure out, well, what's the actual value, and we'll kind of compare it to the approximation. We'll subtract it from the approximation. This is how you like calculate the error. And then we're also going to take the absolute value of it, because we just have to have positive error. So it's just kind of like compares how this tangent line approximation, this linearization, compares to the actual value. So to find the actual value, we would do the sine of 1.25 minus the linearization of 1.25. All right, here's where I'm just going to kind of show you this on the graphing calculator then. So, okay, let's just start with my sine of x curve. Oh, my window's all messed up. Let's just go negative pi to pi. I don't need the full period. And I'm just going to go like negative 2 to 2, because it doesn't go higher than 1. Okay. So remember, you can graph the equation of the tangent line. So if I go second draw, so above the program, draw the tangent line at x is, and you just type in pi over 3, because that's basically what we found in letter A. And here it gives you the equation, so you can kind of compare the stars. We got a slope of 1/2, right? So that's really close. Obviously, and you're smarter than your calculator. Your calculator just approximates derivatives. It can't find exact. And then this is in slope-intercept form, so we can't really compare our constants here unless you were to like distribute this out. Doesn't matter. So we want to find the actual sine of 1.25. So let me see if I can just trace this curve for a second to 1.25. Okay, so that's like pretty close. So if I were to zoom in here on this point, took away my tangent line, Want to approximate what that actually is, and then kind of compare it. I can kind of draw on that tangent line. I don't know exactly where it was. But use that tangent line also to approximate it, and we can kind of compare how close we are. All right, so the sine of 1.25, now that I have it typed in my calculator, I can hit alpha, sine of 1.25. You could also just take the sine of 1.25. That'd probably be just as easy, but good review over stuff you can do with your calculator. We get this value. That's the actual value. Minus what we got for the linear approximation. I only have a final answer. I got about that was like my error. So it's pretty close. I could do this in my calculator to take that minus when I plugged it into my linearization. So that was 1/2. 1.25 minus pi over 3. Anytime I'm doing like radians, like pi over 3, I put those in decimals. Anytime I'm doing fractions, really in general, same with like the square root of 3 over 2 minus that whole thing. There's that number, but we take the absolute value of it because technically we only count the error as like positive. Okay. That's basically all you're going to have to do for a lot of these. I don't even think you have to calculate the error in your homework. I think it's just find the linearization and then compare it to the actual real value, like in a table, similar to this one. Okay. We're just going to do one more. So this one says, find the tangent line approximation T. That's the same as the linearization. Use it to evaluate the graph f at the given point, then complete the table. Okay, so to do part A, find the tangent line. We need two things. We need the slope of the tangent line, which is the derivative at 2. So let's just go ahead and find the derivative. Well, we can do it this way. F prime of 2. F prime of x would be 1/2. Bring that power in front. Drop 1. X to the negative 1/2. 1 over 2 square root of x. There's my derivative, my slope equation. So to find the slope, specifically at 2, I can plug in 2. And I get that. All right, we also need a point, and they actually give us both the x and the y coordinate here, 2 root 2. So to find the equation of the tangent line, point slope form, y minus the square root of 2 equals m, the slope, x minus 2. So there's our equation of the tangent line. Now to make this a linearization, which is the same thing, all you gotta do is solve this for y and rewrite it in the proper notation of the linearization. 1 over 2 root 2 x minus 2 plus the square root 2. Okay, I mentioned this yesterday, but if your book simplifies this further, like if it puts it in slope-intercept form, you don't have to. You can leave it just like this. This is A-OK for AP graders to just leave it like that. Okay, so if you're doing your homework and you notice you still have the same answer, they just want a step further, you can leave it like this. Okay. So now we're just going to use it to evaluate. We will do at that point at 2, and then just point around it. So what I'm going to do, so here's like your f of x. This one's t of x, your tangent line approximation. I call it L of x linearization. That's how you'll see it on the AP exam. Those are the same thing. L of x. I'm going to type f of x, our original function. I'm going to type that into my y1. This one, square root of x. And then I'm going to type in my linearization or my tangent line approximation into y2, and then we can just fill out our table using the table feature in our graphing calculator. Okay, so let's finish this up together. So this one's just the square root of x. Okay. So there's my 1 over 2 root 2. I think I'm going to wrap that in another set of parentheses. So there's the slope times x minus 2 plus square root of 2. It's easier for you to rewrite that in slope-intercept form. You can. I try not to make mistakes. Okay, let's just see what this looks like on a graph for a second. Well, we probably don't need to go all the way out to 10, maybe like 6. Okay, so here's my square root curve. Here's my equation of the tangent line, linearization, tangent line approximation. Those all mean the same thing at 2. 2 root 2 would be the point on that curve, right? At 2 root 2. Okay, so what we're going to do is we're just going to estimate like points around here, and we're going to estimate them on the tangent line or on the linearization and on the actual curve and see like how close they are and why this whole lesson, like concept, like why this works. Okay, so make sure in your table settings you have it to ask, because we're going to type in our own values. Change it to ask, and then you can go to your table, and we can just type these in. We got 1.9 to compare. We got 1.99. We have the actual point of tangency 2, which they should obviously be the same thing at that point, right? Because that's at one point where it touches the curve. We got 2.01, and we got 2.1. And a lot of these look like they're exactly the same, but remember, you can always tab over, and it'll give you a longer approximation. But these two are should be the exact same, that point of tangency, those two. And you can see here that they're very close. Those ones look very similar, and I usually only write the first 4 digits anyway, so let's just kind of copy some of these into our table here. But all right, so for the actual, for 1.9, I just did 1.3784. The tangent line, the linearization, I got 1.3779. Okay, 1.99. Those looked very, very close. The first 4 digits were the same. I can't really fit my dots in here. But we know they're not quite the same after we just looked at that in our table. For 2, let's maybe just make a note that these are the same. Okay, and then 2.01, they look like they're very close. 77. Okay, 1.4491. This table is kind of small. 1.4487. Okay. That's it. That's linearization. can't remember what textbook calls those. Let's see what that person has to say. Okay. It's worded exactly like this. So it's not going to call it linearization. It's going to say tangent line approximation, which is the same thing. All right. That's a wrap. Just basically another application of derivative and how we can use it to estimate points around it. And just knowing, this is probably a good like key concept, knowing that like every curve, if we like look close enough at a point, because that's what calculus is all about. It's like this instantaneous rate of change. What's happening at this specific point, at this specific instant, that everything's like locally linear, okay? Which is why that tangent line's like a good approximation, or how we can like calculate that instantaneous rate of change. Okay, that's all for the lesson. Stop recording.